one more video on single replacement reactions. There's kind of a special reaction that occurs when you use water as a reactant in a single replacement reaction. It says here to use water as HOH. Water tends to split as hydrogen plus 1, hydroxide minus 1. So it's another way of naming water. You could call water hydrogen, hydroxide. You can call water dihydrogen monoxide if you want to get crazy. Now they often say that water is neutral, and it is. A pure sample of water is neutral. Hydrogen ions are always the sign of an acid. Hydroxide is always the sign of a base. Water's got one of each, so a pure sample of water is neutral. So watch what happens when we set up this reaction. Sodium metal and water. And I'm going to write water as HOH, hydrogen hydroxide. Sodium is normally a positive ion, and then hydrogen will be plus 1. Hydroxide, OH minus 1. Hydrogen is positive, so she's interested in switching with, I should say sodium is positive, interested in switching with hydrogen. So we check the reactivity series to make sure that sodium is more reactive than, you betcha, hydrogen. And it's okay that the chart lists hydrogen as H2, and in my reaction it's like a H plus 1 hydrogen ion. Totally fine. Sodium is way more reactive than hydrogen. The bigger the difference between the elements on the reactivity series, the more likely they are to react. This one is definitely a go. We did this reaction back when we were looking at elements and groups on the periodic table. Often the group 1 alkali metals are reactive with water. So we're going to make a switch. We're going to kick out hydrogen with diatomic as an element. In comes sodium to bond with hydroxide. Plus 1, minus 1, it's neutral. Excellent. Okay, so we have to balance this thing. Okay, sodium, sodium, I like that. This really is like 2 hydrogen. Here's 2 and 1 more for 3. And I kind of mentioned I don't like seeing odd numbers, so when I do have an odd number, my gut instinct says double it. Because now I have 4 hydrogen, and I could work with 4. 2 oxygen. Bingo! 2 oxygen. The only thing I got left, I need 2 sodium. And I think we're good. Awesome. Balanced. Last thing I would do is my phase symbols. Sodium is a solid. Water is a liquid. We mentioned that you don't use the L liquid very often. It's only for things that are naturally occurring as liquids. Hydrogen is a gas. Sodium hydroxide is a solution. This will be aqueous. Now when we did this earlier, and in general, people will tell you you can put sodium in water and it explodes or it ignites. It's actually not the sodium that's igniting. The reaction is exothermic, and hydrogen gas is flammable. So if enough energy is released, it's the hydrogen gas that's igniting. Well, what do you know? Okay, so here is the reaction, the correct balanced equation for the reaction of sodium and water. Here is the wrong equation. Now, I often get a complaint. Okay, so this is wrong. Disclaimer. But it's a very common mistake. People will say sodium plus water, H2O. And they think they're following all the rules. Sodium is +1, hydrogen is +1, oxygen is -2. And so they say, okay, let's switch the sodium and the hydrogen. So their products are similar, but there's one difference. They're going to kick out hydrogen, say it's diatomic hydrogen gas, but then they're going to have sodium with oxygen, +1 -2. We need 2 sodium. Here's the difference. In one of them, the product is sodium hydroxide. In the other, the product is sodium oxide. Who's right? So the people in the wrong category, down at the bottom, when they write this equation, they're so frustrated when I mark it wrong. Because they'll say, like, what did I do wrong? I checked everything I'm supposed to. I got the charge on sodium, it's positive. It's going to switch with the positive hydrogen. They'll say, I checked my reactivity series, this is going to work. I got my diatomic hydrogen, then I bonded my sodium with oxygen, I checked my charges. What's wrong with this? I feel your frustration. I kind of get it. Because on paper, what's wrong with it? On paper, that bottom equation looks fine. The problem, when you go to the lab, hydroxides are bases. Anything with hydroxide is a base. So this sodium hydroxide product, this guy is a base. This sodium oxide is not. On paper, they both look great. So how do you know which reaction is right and which one is wrong? You have to run it in the lab and test your products. We're going to do this. We're going to do it twice. We're going to test the properties of the 2 products. We should get flammable hydrogen. That sounds fun. And then we'll check our other product with pH paper or some kind of an acid-base indicator. It will be basic. And that's the only way we know that the true product is sodium hydroxide. So it's as if the sodium really only switches with one of the hydrogen ions, leaving behind hydroxide. Cool. So it's just one of these funky little reactions that you kind of have to be aware of. We're going to run it enough times in the lab that you'll experience the reaction. And hopefully we'll remember this one. Use water as hydrogen hydroxide in a single replacement. Now the other one here is just kind of interesting. This is copper in water, hydrogen hydroxide. Copper's normal charge is +2. Copper can have other charges, but it's most commonly +2. Since it's positive, it's looking to switch with the other positive. So we check the chart. And we will find that this does not work. Copper is less reactive than hydrogen. This is a no reaction. No reaction. Well, duh. I mean, like copper pipes don't chemically react with water. Copper cookware, pots and pans, doesn't react with water. There could be a test question that might say like A, B, C, D. Which of the following metals would be a good choice in forming a container to hold a reactive substance? Well, I'd probably want my container to be non-reactive, right? I wouldn't want to make a container out of like calcium or sodium. They're highly reactive metals. Maybe something like copper, silver, platinum, gold. I guess if money wasn't an option. Maybe not mercury, because that'd be a liquid and that's toxic, but the idea is that if you wanted to store something reactive, you would want to choose something non-reactive as your storage material. You can put copper pennies in a wishing well and they don't light on fire. Copper is less reactive than hydrogen. No reaction.